Hello everyone. This is topic 9, derivatives of log and exponential functions with bases other than e. So now we look at a situation, we start with the theorem, where a is a real number. So instead of e as a base, we're going to use a. And we have a standard disclaimer to let you be a differentiable function of x. So here are two new formulas. You won't have to memorize them. I would supply you with them if I'm going to test you on them. Basically, just know they exist. Okay. And this is a situation that we don't encounter that often. So when you see a base other than e, just know to reference these formulas. And they're very similar to our formulas for like e to the u, for example. E to the u is e to the u and then du dx, but for a to the u, we get this extra natural log of a as a factor. And similarly, differentiating log base e of u, that would be the natural log of u, we'd get u in the denominator and its derivative in the numerator. But turns out if the base is a, we get this little modifying factor of 1 over the natural log of a. So we'll show through proof how that occurs. That is the extra factor natural log of a and the extra factor of 1 over the natural log of a. And those proofs we'll have a proof quiz on, and I will make you aware of that in class. But just some quick examples on using the formulas. I'm not really going to test you on these because, again, you don't encounter them too often. But realize when you see a base other than e, reference these formulas. This particular one fits the form for a to the u, and it's just a basic application of the formula. dy dx would be, just follow the formula. It says the natural log of a in this case is 5, so the natural log of 5 times, and then the rest of it is just like differentiating e to the u. That is, recopy 5 to the 1 minus x cubed, and then the derivative of the power on the base, and that would be minus 3x squared. So with regards to the formula, there is the natural log of a times or e to the u, and then the minus 3x squared represents the du dx. So cleaning this up, we bring the minus 3x squared out in front of the natural log of 5, but you do actually need the multiplication symbol in there to separate the factors. And then the factor of 5 to the 1 minus x cubed power. Okay, so to the next example, that's showing the formula for log base a of u. A in this case is 3. So just match it up, follow along with the formula. The derivative, let me note that this is log base a of u. And so therefore the derivative dy dx, it's 1 over natural log of a is 3 in this case, and then times the rest of it is just like differentiating natural log of u. U goes in the denominator, that's 1 minus x squared minus 2x in the numerator. So with respect to the formula, there's 1 over natural log of a, and then times u in the denominator and the du dx in the numerator. I'll just clean it up off to the right here. Make it a single fraction where it is minus 2x, and it would be important to bring the 1 minus x squared out in front of the natural log of 3. Because if you wrote it in the opposite order, excuse me, then it would be misconstrued as to what the argument of the log is. And the only argument of the log, natural log there, is the number 3. Okay, so we could involve these formulas with products, quotients, powers, trig functions, and all sorts of things, but I just want to make sure that you know that these formulas exist and know to reference them when needed. But to satisfy our curriculum, we're going to go through the proofs, and again, you'll be asked to prove these on a proof quiz. And for the derivative of a to the u, we start off the same way that we did when we proved the derivative of e to the u. That is, we use logarithmic differentiation. So we start with the given, let y equal a to the u. And logarithmic differentiation, we take the natural log of both sides. So natural log of y equals the natural log of a to the u. And there's nothing we could do on the left-hand side, but we can simplify the right-hand side by using our power property for logarithms, our algebraic power property. So the natural log of y would be u times the natural log of a. Now, at that point, you don't have to do this, but I'm going to do something, and I'm going to reverse the order of the natural log of a and u. So instead of u natural log of a, I'm going to write it as the natural log of a and then times u. And now I'm going to start the differentiation process. And it is implicit differentiation, so I'm going to introduce the ddx notation. Remember, this is optional. You don't have to use it. You can jump right in there and start the differentiation process without it. It's just the differential operator, as we know. And it's not dy dx, it's ddx, indicating that we're about to differentiate implicitly with respect to x. And we've done this many times, differentiating the natural log of y implicitly with respect to x. Log goes away, we get a fraction, y in the denominator, its derivative, dy dx in the numerator. And one of the reasons why I rewrote this by using the commutative law of multiplication and putting the natural log of a first is because the natural log of a is just a constant. Because we claimed that a was a real number. So no matter what a is, the natural log of a is just another number. And so that's going to tag along in the differentiation process, just like any other number, like, let's say 5 or 7 or 3, whatever. So that tags along, and then the derivative with respect to x of u is just simply du dx. Okay, and then we'll solve for dy dx by multiplying both sides by y. You can indicate that if you like I did in red, not necessary, it's understood that if you multiply both sides by y, any reader should know what you're doing. And I think I'm going to position it so that it's right in between the natural log of a and du dx. So I'll write natural log of a times y times du dx. And the reason why I put it there was because when I back substitute, because that's our last step, is back substituting. So I'll bring it just off, kind of off to the side here. Last step is your back substitution, and that's the way the formula was written, with the a to the u between the natural log of a and du dx, and that's what y is, a to the u. So we get natural log of a times a to the u, and then our du dx. Okay, and that would end the proof. Alright, now to prove the formula for the derivative of log base a of u, we actually need a familiar formula from pre-calculus or algebra and trig. It's referred to as the change of base theorem. And you can actually take any logarithm and change the base to any number that you want. So the disclaimers are just to let a and b be real numbers. And if you have log base a of x, you could turn that into the logarithm of any base you want. But there's a little compensation. Notice that we changed the base to b, so we said log base b of x. but then divided by log base b of the old base a. So to prove this one, what we're going to do is we're going to let y be equal to the left-hand side, log base a of x. And then what we're going to try to do is manipulate this and show that y is also equal to the right-hand side. Now, recall the definition of logarithms. This was way back. I'm going to write it in opposite color here. Well, it's not an opposite color, it's just a different color. We said log base b of n equals x if and only if you take the base b, raise it to the x power, and you get the number n. So by definition of logs, by that definition, we take the base, in this case of a, raise it to the y power to get the number x. Alright, and then what we're going to do is we're going to take log base b of both sides. So log base b of a to the y would be log base b of x. And at that point, we'll exercise our algebraic log property for log of a power and bring the y out in the front of log base b of a will equal log base b of x. And then we're just simply going to divide both sides by log base b of a. If you want to show that, I'm showing it in red here. And so now we have that y is equal to log base b of x over log base b of a. And that basically proves it, because we've shown that y is the right-hand side, and we had started with y equaling the left-hand side. But if you want to make one more final statement and replace y by what it was originally defined to be, log base a of x, then we have proven that log base a of x equals log base b of x over log base b of a. And that formally ends the proof. Okay, so then the final proof, there's going to be 3 proofs on this little proof quiz. The 2 we just went over, and then the final one here. And this is proving the derivative of the log base a of u. Now, I wrote it out using, instead of using our shorthand notation of the ddx differential operator, I wrote it out more formally, stating that if y is log base a of u, then this is what we want to prove. And that's because that's how we started, and it's more convenient to prove it that way. So we have the little disclaimers, don't worry about them, but a is real, use a differentiable function of x. And we start with the given. So we're going to let y equal log base a of u. Alright, so then what we do is we use the change of base theorem. So by change of base theorem, if you want to write it, we're going to change the base of a to a different base. And you probably should know what base we would choose, because, well, look at the formula. The formula contains a natural log, and the natural log is a base of e. So, Euler again. And so we change the base to e. So by them, it's log to the new base, e, of u, over log to the new base, e, of the old base, a. log base e, of course, is expressed as the natural log. So y is the natural log of u over the natural log of a. And then I'm going to rewrite this because u is the variable, a is a real number, so I'm going to write it as 1 over the natural log of a, and then times the natural log of u. And the reason why I did that is because just like in the last proof, that is the first proof, when a was a constant, the natural log of a was a constant, and so it follows that 1 over the natural log of a will also be a constant. And that's just going to tag along in the differentiation process. Just like any other number, like 5 or 7 or 4, whatever. So now we can differentiate. We're differentiating with respect to x, so I suppose if you want to throw the d dx notation in front of each side here. But again, realize that 1 over the natural log of a is a constant. So on the left we get dy dx. On the right, 1 over natural log of a just tags along as a constant multiple. And then we have times differentiating the natural log of u. That's already been proven to be a fraction with u in the denominator and the derivative of u denoted by du dx in the numerator. And so that would end the proof. Okay, so 3 nice mechanical proofs. And then we just have one quick topic left, topic 11, integrating exponential functions with bases other than e. And so we'll finish that up quickly here. It's basically just reversing the differentiation rule that we just established. That is, if we have the derivative formula for a to the u is natural log of a times a to the u times du dx, but we want to reverse that, so all we're doing is think about integration as anti-differentiation, and we want to reverse that. Let's ignore the natural log of a and just consider integrating a to the u. We're going to get back a to the u, but if we ignored the natural log of a in the differentiation, when we reverse the process, we get 1 over the natural log of a times a to the u. So, once again, these formulas we do not encounter very often. And so, when you see a funny base other than e, just make sure you know there are formulas out there, and look back and reference these as necessary. But just one quick example, and I'm not going to test you on this concept, but just to show the idea, works the same way as e to the u. That is, consider 7 as your base of a, and this fitting the form of a to the u requires a u substitution, where we pick u to be 1 minus x cubed. Differential du would be minus 3x squared. And the differential dx formally, of course, and we modify by the negative 3, so negative 1/3 du is x squared dx. And when we go back to the integral, we've already accounted for a to the u. We look at the leftover factors, x squared, differential dx, compare them to our du. No surprise they match in this case, just modified by the negative 1/3. So replace those factors by negative 1/3 du, and we fit the basic formula most efficiently, bring out the negative 1/3, and upon the change of variables we have the basic formula for the integral of a to the u with respect to u. And so we'll integrate, and we get 1 over the natural, so just follow the formula. Get 1 over the natural log of a times our a to to the u plus or constant, and then we'll put back our a. I guess I probably should have stated, maybe off to the side here, that this is also where a is equal to 7. So that's our base. So we get negative 1/3 times, oops, sorry about that, 1 over natural log of 7 times 7 to the, put back our u was 1 minus x cubed, and then plus our constant. So if you want to make this a single fraction, I don't know, I'd probably just leave it as negative 1 over 3 natural log 7, and then times the 7 to the 1 minus x cubed. Or you could put the 7 to the 1 minus x cubed in the numerator, it's your choice, and then plus our constant. Okay, so that's the end of the material for the first exam. So we have a review sheet, and I'm going to make some videos of selected problems from that review. So if you care to watch these videos, I'm obviously going to do them in class as well, but if you care to watch these videos, they will be available to you also. So we'll see you when you are ready.